In this video, we're going to talk about functions in two variables. We may even mention functions with more than two variables, but I want to define what I'm talking about when we talk about multivariable functions. When we first encountered functions and variables, we pretty much said that if it is represented by a letter that can take on different values, then the letter is a variable. But there are two kinds of variables that might appear in a function. One is the independent variable and one is the dependent variable. We can change the independent variable and there will be a resulting change in the dependent variable. Typically, we have confined ourselves to equations and functions that have a single independent variable and a single dependent variable. These are actually functions of a single variable because when I talk about these multiple variables, I'm really talking about how many independent variables I have. If I limit myself to a single independent variable, then I have to constrain the conditions of my problem to be idealized. In other words, if I'm doing a physics problem, I have to ignore things like friction or air resistance or wind shear. A function of two or more variables will have more than one independent variable, but still only one dependent variable. So for example, I might want to know how temperature in an ideal gas will increase if I increase the pressure on the gas by compressing the volume with a plunger. This is an example of a problem where I have two conditions that can change, two independent variables, and evaluating what happens to that third variable, the dependent variable, is the problem I need to solve. A function of two variables is explicitly given by z is equal to f of xy, or I might express it as capital F of xyz is equal to 0. The z is the dependent variable. That gives me x and y as my independent variables. A function given by z is equal to f of xy will assign to each point xy in a set D that exists in my two-dimensional space a unique real number z in a subset of R in one dimension. The set D is the domain of my function f. The range of f is the set of real numbers z that z takes on as the points x, y vary over the domain. Just like my functions in a single variable, a multivariable function may have a domain that needs to be restricted by the context of my problem. For example, I may be interested in a problem where one of my independent variables represents the volume of a liquid, and the other independent variable represents the surface area of a container for the liquid. The domain for this problem would have to be restricted to non-negative values for both volume and surface area because I'm not going to have a negative volume or a negative surface area. Let's work some examples. I want to find the domain for each of the following functions. The first function is given by f of xy is equal to the cosine of the quantity x squared minus y squared. The second function is given by f of xy is equal to 12 divided by the quantity y squared minus x squared. In the first case, f of xy is equal to the cosine of the quantity x squared minus y squared. Note that my cosine function is defined for all real values of the argument. That means that for all real values of x and y, my cosine will be defined. This gives me a domain of all real numbers in two-dimensional space, or I might state that as all R2. In the second case, I have f of xy is equal to 12 divided by the quantity y squared minus x squared. This function will not be defined whenever x is equal to either plus or minus y. This means that my domain in R2 space will be the set of all xy, provided x is not equal to plus or minus y. The graphs of functions in two variables will be a little bit different as well. Keep in mind that I actually have two independent variables and one dependent variable when I'm talking about a graph of function in two variables. In other words, I'm talking about an equation given by z is equal to f of xy. This equation has two independent variables, they're x and y, and for each point x and y in the domain of the function f, I will have a point given by the ordered triple x, y, f of xy, and this ordered triple point will lie on the graph of f. A relation can have the form capital F of xyz is equal to 0. This will have similar definitions in terms of domain and the value that my z variable will take on. Just like my functions in one variable, functions of two variables also have to pass a vertical line test. This means that a relation in the form of capital F of xyz will only be a function as long as every line that's parallel to the z-axis intersects the graph of capital F once and only once. Graphs that don't behave as functions include an ellipsoid, a hyperbolic paraboloid that lies on its side, or an elliptic cone. Graphs that will behave as functions will include things like the elliptic paraboloid or a hyperbolic paraboloid that is aligned vertically. Let's work another example. Here I want to match each function with the correct surface graph. The first function is f of xy is equal to sine of the product of x and y. The second function, f of xy, is equal to 1 over the product of xy. The third is the function f of xy is equal to the natural log of the product of x and y. And the fourth is f of xy is equal to 1 over the quantity x squared plus y plus 1. These graphs are fairly complicated and extremely difficult to describe, but we can get a lot of information from the function itself to help us determine which of the graphs will most appropriately match the function itself. The first function, f of xy is equal to sine of xy, is a function that is continuous for all real numbers of x and y. The function will oscillate between positive and negative values over the entire domain, but it will be continuous. This means that the first function, f of xy is equal to sine of xy, is going to match the function that oscillates and is continuous. The second function, f of xy is equal to 1 over the product of x and y, is a rational function where the denominator is the product of x and y. In this case, neither x nor y can be 0 because my function would be undefined. This means that I have to have an asymptotic plane that will correspond to the xz plane and another one that will correspond to the yz plane to prevent x and y from ever equaling 0. There will also be a horizontal asymptotic plane that coincides with the xy plane because my function is not going to change sign in the middle. This means I'm looking for a graph that has 4 distinct surface regions, 2 of which will be above the xy plane when the signs of x and y are both the same, and 2 of which will be below the xy plane when the signs of x and y are different. So that my second function is going to be the graph with the 4 distinct pieces of the surface, 2 above the xy plane and 2 below the xy plane. My third function, f of xy, is equal to the natural log of xy. In this case, neither x nor y can be 0, but I cannot have x and y with differing signs. This means I'm looking for a graph in which the surface will exist in regions where x and y have the same sign. This will be a surface graph that has two pieces to it, one where x and y are both negative and one where x and y are both positive. This graph is going to be the graph that has the two pieces that cross through the second and fourth quadrants in the xy plane. My third function, f of xy, is equal to 1 over the quantity x squared plus y plus 1. Of course, this is going to match the final graph that I have, but let's look at what that function is telling us. That function is 1 over something that is quadratic in form. I'm going to be looking for a graph that has something that resembles a parabolic arc to it. And notice that when x is positive or negative, the x squared will always be positive, so that this will only be negative when y is negative and greater than x squared plus 1. It will be positive everywhere else. So I'm going to have two regions, one that's a fairly large region that lies above the xy plane, and one that's a smaller region that lies below the xy plane. This final function is going to match the graph with two parts and a parabolic arc. So now you get to try it. Pause the video and sketch the graph of the relation described by capital F of xy is equal to the square root of the quantity 1 minus x squared minus y squared. Identify the surface, state the domain and range, and indicate whether the relation is a function or not. When you're ready, restart the video to check your understanding. The first thing I'm going to do is evaluate the expression for my relation. The relation f of xy is equal to the square root of the quantity 1 minus x squared minus y squared requires that my argument under the radical has to be greater than or equal to 0. If I rearrange the discriminant just a little bit, I get an inequality that says x squared plus y squared is less than or equal to 1. This tells me that my surface is going to be a hemisphere of radius 1 centered at the origin. This makes it fairly simple to graph in a 3D coordinate system. Now I want to check it with the vertical line test. By the vertical line test, I can see that this surface is going to be a function because all lines parallel to z will intersect the surface at most one time. The domain of my function will be all xy such that x squared plus y squared is less than or equal to 1, and my range will be the set of values between 0 and 1 inclusively. This is how I can begin working with functions of two independent variables. Be sure and let me know if you have any questions.